Okay, so I've got a task for you to warm up with. I'll put you in groups in a moment. So remember last time we talked about Eulerian graphs, Hamiltonian graphs. Eulerian is where we can go around the graph and cover every edge. Hamiltonian is we're looking for a cycle where we can start at one vertex, go around, hit every vertex, and return to our starting point. Hamiltonian doesn't care about covering any edge. It just cares about covering all of the vertices. Eulerian cares about covering every edge. Doesn't matter if we hit a vertex more than once. So I'll put you in groups, and the question is, I've got two sets. So A is the surrounded by the black box. It's like the L shaped, and then B is the purple box. And I want to know because I took these from the internet and then I forgot which ones were which. And so I would like to make you figure out which ones are which. Okay, so you guys have said that A is what? Hamiltonian? That means B is Eulerian. All right. And yeah, so however you pronounce that word, this graph and the the wheel on 5 vertices, those are our biggest clues. Where when we talked about Eulerian graphs, there's the theorem which says if it has no vertices of odd degree, then it's Eulerian. There's a cycle. If it has exactly two of odd degree, then there's a path that satisfies Eulerian. It just doesn't start and stop at the same place. And so when we look at these graphs, so like the wheel on 5 vertices, this vertex has degree 3. This has degree 3. So does this one. So does this one. That's more than 2. And so therefore, this graph in particular cannot be Eulerian. And similarly, this graph has 1, 2, 3, also 4. 4 is not 2. And so because of that, this set of graphs can't be Eulerian. Now, some of these graphs are, like C4 certainly is Eulerian, but it's just that not all of these graphs are. And so we could go through and prove for each of these that what's the degree of all of the vertices? Are there any odd vertices? That's how we would reason about it. Okay. So I just want to mention grading. I'm aware I'm very behind. I have blocked off like 3 hours of my afternoon to sit down and grade things. So fingers crossed I get things back to you by Wednesday. I'm working on it. And the other thing I want to mention is research. So in this class, you've done a lot of work in writing proofs, learning how to count, and now in graph theory. And I just want to say that my line of research involves graph theory and a lot of technical writing. So if you're interested in doing something like this for an actual project, come talk with me. I'm here over Jan term if you're interested in having meetings and working on a project. I'm going to be writing a journal paper. So if you want to help with that, then come talk with me. I know there's also summer research, but for me, research is year round. And so if you're interested in joining a project, I'd love to talk with you about it. Okay. So today we're going to gain the skills to answer the fish question. So we're going to first talk about how do we plan meetings? How do we allocate registers? We'll talk about jerseys, and then we'll talk about maps. So today we're talking about vertex colorings. And so this is a term. So the fun thing about this class is it's kind of like kindergarten, where first we learn how to write things, then we learn how to count things. Now, and then we connect the dots, and now we're learning about how to color things and also conflict resolution. So this is really kindergarten for mathematicians. And so we're going to talk about how to solve conflict problems. And the way we're going to do that is with what the textbook calls an interference. That's not how you spell interference. An interference graph, where our objects, our vertices are going to be things that can interfere, and an edge means there is some interference. Again, just to remember that, let's say we have like the butterfly graph. That is the same as if we drew the graph kind of like this, right? The positions of our graph don't matter. These two are isomorphic. This is just a reminder as we're going forward. The positions of our vertices, I truly could not care less. All right, so we've got 5 people: Anderson, Baker, Charles, Darwin, and Ebert, and they need to attend 4 committee meetings, but not all of them have to be at the same meetings. And we're trying to schedule them for these 4 hours in the afternoon. So if we've got some meetings, maybe some of them can happen at the same time, others can't. So for example, committee 1 cannot meet at the same time as committee 3 because Anderson is in both committees. Similarly, Charles and Ebert, or Charles can't be in, so Charles has to be in committee 2 and committee 4. And so those can't happen at the same time because Charles cannot be in 2 places at once. So the way we solve this sort of problem is by representing it as a graph. And so when we do that, we need to decide what are the vertices, what are the edges, and we need to be very clear about this. So as I see it, we kind of have 2 options. One option is the people are the vertices. The other option is the committees are the vertices. Think about it for a second. Which makes more sense? All right, who votes for the people being the vertices? Okay, 2, 3 votes for. Who votes for the committees being? 1, 2, 3, 4. Okay, so I'm going to choose, so because this is conflict resolution, I'm going to choose the things that actually conflict. So as in, this committee cannot happen at the same time as the other committee. It's not that choosing the committee is, how do I want to say this? If you choose the people, it can still get you to the right answer. It just may not be the simplest, most straightforward way. Question?
That was my question. I was like, what would be the point of doing the people? Because how could you like indicate that they were sections?
Right. So yeah, so that may be of like, how do we represent that these people are on the same committee? So it's just different ways to approach this. And so if you take the 374 next semester, we'll talk about graph algorithms, and some of these, like, simplicity and conciseness are really the goal in constructing solutions to these kinds of problems. Okay, so let's say the committees are the vertices. So then what are the edges? What do the edges represent in our problem? Yeah. People in what way?
Person A, city 1, 2, 3, and 3
Mm-hmm.
that edge would represent.
So let's say committees I and J have people in common, leads to I and J to be in our set of edges. So being super explicit about what an edge means. So an edge is a pair of two vertices. And so committee 1 and committee 4 have Darwin in common. And so there has to be an edge between 1 and 4. Okay, so once we've decided the structure of our graph, once we've decided what the vertices and the edges are, now we can draw it. So let's say we're going to call this committee 1, committee 2, committee 3, and committee 4. Again, it doesn't, you can draw 4 vertices however you want. The placement doesn't matter. So now let's insert our edges. So let's look at 1 and 2. 1 and 2 have a conflict over Ebert. So they can't happen at the same time. Let's take 1 and 3. 1 and 3 both have, what's his name, Anderson. So there's an edge between those. 1 and 4 have a conflict over Darwin. Okay, so for 1 and 2, we've already done that. For 2 and 3, looks like no conflict. For 2 and 4, CE and CD, so Charles is a conflict. And then finally to check 3 and 4, A, B, C, D, no conflict there. Okay, so we've got our graph. Have we solved the problem? Not really. So we've got a nice representation of this is how our committees look, but we don't have like, what's our schedule of meetings? So we need that. Here's where vertex coloring comes in. So this process is, I'm going to go through and color each vertex, and I'm going to do so in a way that no 2 adjacent vertices get the same color. So we're going to color each vertex. No 2 adjacent get the same color. So this is where your colored pencils come in. And so there's lots of places we can start with. So I'm going to start, I don't know, with 1. And so I can color 1 red. And once I do that, that means that 2 and 4, by my definition, cannot also be red because 2, 3, and 4 are all adjacent to 1, and so they cannot be the same color. So that means, so let's go to 2. Let's make 2 purple's my next color up. So I'll color that purple. If we go to 4, then can 4 be red? No. Can 4 be purple? No, because 4 is adjacent to 2. So now we've got to use a new color. So green's up next for me, so I'll use green. And then when we look at 3, can 3 be red? Can 3 be purple? Could 3 be green? Yeah, so doesn't matter which one. I'll just choose purple. Because 3 is not adjacent to anything purple. And so the goal here, because like we're scheduling committees in this 4-hour block in the afternoon, and we don't want to go until like 6 or midnight. So we don't have infinite amount of time to schedule these meetings. So we want to be as conservative in our number of blocks needed as possible. And so I'll add this to this. Use as few colors as possible. I'll move the label for up there. So we want to use as few as we can. And so we still have, so like we've made progress on our goal, but we still haven't exactly determined an exact answer. So what this tells us is that we can have committee 1 in one block, then we can have committee 4 in another block, and then 2 and 3 can happen in the same block. Note that we could have chosen so we chose 2 and 3 to happen in the same block. We could have chosen 3 and 4 to happen in the same block because there's no conflict with either of them. And so this is just a tiebreaker. So let's see. So on the hour starting at noon, so we can say that 12 p.m. is committee 1. We could say that 1 p.m. is, I don't know, 2 and 3. And then 2 p.m. can be committee 4. And so there's 3 slots that are needed. And now we have answered the question. We've said, here's how many slots are needed. And then given, for example, you could choose 1 by itself, 2 and 3 by itself, and then 4. Question?
If we were to answer a problem like this on saying homework isn't us, what
Mhm.
should we do? Should we like, because the graph isn't answer enough, should we fill it in like using the stuff that are provided, like you with the time blocks, like writing out 12-1?
Okay, so like the 12, 1, and 2, I got from the problem where scheduled on the hour starting at noon. But the real question is how many meeting times must be arranged? And so that's like the real answer is 3, but I've given a sample configuration. And so once you get here, the number of colors that you use to color the graph gives you the solution. But it absolutely relies on a careful reading of the question. Okay, so let's talk about some definitions. So the way we have colored this graph is what we call a vertex coloring. And so we can say that a vertex coloring is proper if, so let's say of G, and we'll say we used K colors. And we have assigned each vertex a color. And then here comes our definition where if vertices are adjacent, they can't get the same color. So each adjacent vertex don't get the same assignment, they get something different. And if you don't have colored pencils, what we could have done instead is, so we've labeled these vertices 1, 2, 3, 4. So maybe we could have said or we've labeled them 1, like 2 and 3. We could have said A, B, and C. So just some other different numbering scheme to say 1 is associated with A, or the red is associated with A, purple is associated with B, green is associated with C. So it's possible to do this without colors, but we call it vertex coloring. So actually coloring it makes it more fun. Okay, so that's a proper vertex coloring. And once we do that, we say that, so once there is a vertex coloring, so if G has a proper vertex coloring, we say G is K colorable. So for our example, we colored G with red, purple, and green. That's 3 colors. So we say that G is 3 colorable. So that's our definition there. And then we have a term for the chromatic number of G, which we denote as this thing that looks like a fancy X, but is actually, I'm not sure if it's a capital or a lowercase pi. Okay, so that's \CHI, all lowercase. I'm gonna run out of room. Is the smallest possible value of K. All right. So yeah, so our goal is to use the smallest possible number of colors. For our example, we could have assigned 3 to be blue. But that's not the smallest number that we could find. And so we would not say that the chromatic number is 4. We could say that G is 4 colorable because here's G with 4 colors. But that's not the chromatic number. The chromatic number is the smallest possible amount of colors that we could possibly use to color this graph. If you're curious on how exactly we do this, that's an algorithm question. And so I encourage you to take 374 and we'll talk about it. All right, so I've got a question for you that to those of you in computer systems might look a little bit familiar, so in computer science, we have this way of optimizing called register allocation, where we've got variables and we need to store them in a way that we can access them quickly. And so for the registers, we don't necessarily want to assign them to the same register. Some we want to assign to different registers. Variables in the same register may not be accessed at the same time without corrupting their values. So if we want to use 2 variables at the same time, they cannot live in the same register. And so let's suppose we have 1, 2, 3, 4, 5, 6, 7 variables named with letters, and they're used in a 6-step program. So the numbers are the steps of the program. The letters are the variables. And I would like to know, how many registers do I need? So first step is create a graph. The second step is to color it. The third and fourth step is what does a color mean in this situation? And then what's the chromatic number of the graph? Any questions on the problem? Okay. All right. Here, let's put you back in your groups for a few minutes and think about this. All right. Very good. Thank you very much. So, oh, I have space for the solution. I planned ahead. All right. B, D, E, F, and G. Okay, so A has an edge between B, C, not D, E, F, and G. B has an edge to C, D, E, F, and G. C has an additional edge to D, E, F, and G. D, that's about it. E, we've got C, B, and A. There's an additional one to G. F is all good. G is all good. Okay, so the first step is to draw the graph. The good news is that the problem specified, here's how you're going to draw the graph, where each variable is, or each vertex is a variable, and an edge means that there's some conflict in the steps. So there's an edge between A and B because two conflicts. Okay, the next step is to give the graph a proper vertex coloring. So to start with, some of you found 5 at first, some of you found 4. And so using the book as my guide, because we want to cover some other things. So if we color A red, that means that now, like, none of the things that it's adjacent to can also be red. Something I want you to notice is consider the subgraph of A, B, C, and G. If we draw that, so A is adjacent to all of them, B is adjacent to all of them, C is also adjacent to all of them. So we have found a complete graph in our, as a subgraph of our original graph. This is also called a clique or possibly clique, which is basically a complete subgraph. Having a complete graph as a subgraph means that if we color A one color, none of the others can have the same color. So we at least have a chromatic number of 4. Of maybe there's others that we're looking at, but it cannot be less than 4 because we have this as a subgraph. So let's color B purple. Let's say C is green and G is blue. and let's see how we can solve the rest of them. So F not adjacent to G, we'll make that blue. E wait. I think that might be okay, it's really hard to tell in the book. Hold on. Let's look at the book. Okay. Doesn't B and E look like the same color? Right, I think, but like B and E, 2, 4, 6, 3, 5. Oh wait, no, that's a mistake. B has lines 2, 4, and 6. E has line 3 and 5. There's no overlap there. Serves me right for copying from the book. Okay, let's very carefully. Okay, let's erase that and then fix problems. Okay, edge between E and C. Da, 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 da. Okay, hooray, we found an error. This means that we can in fact color E as purple, and then D, yeah, could be blue, could be red. I think the book colors it the equivalent of red, but that's fine. Again, it's just tie breaking. Yeah,
It's just be between F and
between F and D. Yeah. Man, what a time. Okay, so D cannot be blue then, so D has to be red. Okay, so that's wrong. And that's missing. I'll check in the errata later, see if that's okay. So to answer the other, so we've done part 1 of draw the graph. We did it incorrectly at first. Part 2 is give it a coloring. We have given it a color. Great. And then what does each color represent? What do we think? Bringing it back to the original formulation of the problem. Yeah, so like which register can we assign these variables? So
Right.
register, and then what is the value of the chromatic number of G? How does it apply to this problem? And so because of this notion of the clique, this for clique, we say that the chromatic number of G, so it's at least 4, and we have found that there is a 4 coloring. Therefore, the chromatic number is 4. Okay, questions on that before we move on? Cool. Okay, let me just write. So this means the chromatic number of G has to be greater than or equal to 4 because this is a 4 clique, a clique on 4 vertices. And so the lower bound is 4, and then we found a coloring using 4 colors. And so because of that, we say that the chromatic number is 4. All right, so let's try and find some solutions. So like, what's the chromatic number of some graph? So I'd like you to think about it for a moment. What if G has at least one vertex? What if G has at least one edge? What if it's complete? Or what if it's a cycle? Think about it for a second.
The line slightly go cycles.
A cycle. It's like a path if we brought it back together at the end. Okay. First one's kind of a trick question. If we don't have any vertices, what's the chromatic number of our graph? No vertices, 0. If there's at least one vertex, what can we say about the chromatic number? Yeah, at least one. So chi of G is greater than or equal to 1, which seems boring, but hey, there we go. So if G has at least one edge, what can we say about the chromatic number? Yeah? Yeah, so we've got at least 2 vertices joined by an edge, at the very least. So that means the chromatic number has to be at least 2. All right, so what if we have a complete graph? Why?
Because each vertex is connected to every other vertex, so each individual one has to be its own color.
Yes, that's the main idea. So that's like when we talk about the clique. So the complete graph on 4 vertices, each of these are adjacent to each of the other ones. And so we cannot reuse colors. It's just not possible. And so it is, in fact, equal to n. And it can't be, so it can't be less than because that's not possible given our definitions. It also can't be greater than because why would it be? We've got n vertices. All right, what about our cycles? What do you think? Yeah.
2 linear cycles, 3 first.
How come?
Well, you. Cycle, all have before. And if you have an odd cycle, you're gonna, like, kind of end back up on the same.
Yeah, that's correct. So let's, if we choose red and purple, and then we can just alternate as we go around. And because it's divisible by 2, so that works out fine. But if we do that, so we can alternate most of the way, but then we get to that, the thing in the middle that breaks the tie. And so in this case, we do have to use a separate color. Cool. All right, we have run out of time to do this problem. I have a question of, I'm making a D&D map, and I want to color every adjacent region independently. So like, if I color A green, B can't be green because they're right next to each other, and I don't like the way that looks. G also can't be green, nor can C. And so this ends up being, again, a coloring problem, where we can say that the vertices, I'm gonna have to erase that now. The vertices of the graph are the regions of the map. So we can say this is A, and I want to join them by an edge if they cannot be the same color. So B is adjacent to C and D, which shares an edge with E and F. Then we've got G over here. And so I can do it this way. So I'll spare you the coloring. But I want to mention that this is a special kind of graph. This is a kind of graph that we call planar. And planar means this is a way of drawing G such that no edge overlaps. So for example, this graph we call planar. There's no edge crossing. Let's draw K4. This graph, K4, is planar. We could draw it in a way that is not planar, so where those two edges cross in the middle, but there's a way of drawing it so that it is planar. So if such way exists, we say that G is planar. If we cannot find a way of drawing G where the lines don't cross, then we say that G is not planar. And there's a theorem called the four-color theorem, which says that if G is planar, then the chromatic number of G has to be less than or equal to 4. It's got a super interesting history. We'll resume here next time. Thank you, and I will see you on Wednesday.